Hello students! So there is only a single goal that I have today. I want to go through one example of proving that a single sequence of functions is uniformly Cauchy and using that to make a conclusion. So let's go ahead and get started. This is page 179, I believe, in the notes. Let's do it. So here we go. So here is the goal. Let h sub n be the function given by the formula h sub n of x equal to the sum from k equals 1 up to n of x to the k divided by k. The claim is, I'm going to try to follow the same warning as is in there even, prove that the sequence of functions h sub n is uniformly Cauchy on negative 1/2 to 1/2. So there's my goal. Let's go ahead and see what it is that we want to show. So this will be scratch walk off to the side. So we want to show that for all epsilon greater than 0, there exists a trace of big N independent of x, such that for all x in U, and for all little n bigger than big N, absolute value of h sub n of x minus h sub m of x is less than epsilon. Oh, and by U, I of course mean what the domain actually is. Negative 1/2 to 1/2. So let's try to do some scratch walk. Let's just try to analyze this piece. Let's try to analyze absolute value of h sub n of x minus h sub m of x. Well, I have a formula, right? H sub n of x is the sum from k equals 1 to n of x to the k divided by k. That's just a stray mark. There we go. Minus h sub m of x. Well, I know what h sub m of x is. It's the sum from k equals 1 up to m of x to the k divided by k factorial. So let's just mess around with this. Oh, nope, no factorial there. So the first thing I notice is that these sums have lots of terms in common. So let's go ahead and add an assumption. Let's assume that little n is bigger than little m, maybe just bigger than or equal to. So that I can cancel most of the, well, all but the last n minus m terms in the sum. So canceling all the common terms, I'll be left with the sum from k equals m plus 1 up to n of x to the k divided by k. Alright, this should seem like it's getting pretty familiar. You remember how we showed that certain series converge? This should seem familiar to that. That'll be less than or equal to, by the triangle inequality, the sum from k equals m plus 1 up to n of x to the k divided by k. Oh, but in fact that's exactly the same as the sum of absolute value of x to the k divided by k. And now, well, check this out. I know that x is in between negative 1/2 and 1/2. So let's use that. So that means this quantity will be less than or equal to the sum of a bunch of things that look like 1/2 to the k divided by k. And this is starting to look like the thing you would need to analyze to study a geometric series, except that there's a k in the denominator. But dividing a thing by k is just going to make it smaller. So I can make it bigger by just erasing the k. Wrong color. The sum of 1/2 to the k, because each of those k's is bigger than or equal to 1. Oh, neato. So that's the sum from k equals m plus 1 up to n. Now, as a hint provided in the statement in the notes, was to use the fact that un, the sum from k equals 1 to n, that of 1 over 2 to the k, that sequence of real numbers is Cauchy. Well, this looks like it has to do with that, right? That's less than or equal to. Nope, that's exactly equal to the sum from k equals 1 up to n of 1 over 2 to the k minus the sum from k equals 1 up to m of 1 over 2 to the k. But that's exactly that. Now notice that everything in sight is positive. You can put these absolute value bars back. You wouldn't lose anything. You can put it back right here. Oh, but check it out. An assumption given is that this thing is Cauchy, so that's less than epsilon. So that gives us the proof. It also tells us maybe a good place to start. Right? If you want to prove that a thing is Cauchy, you want to say for any epsilon there exists some big N such that some stuff happens. And it looks like the stuff that we need that big N to give us is that. So let's go ahead and get started. Let's now write down the actual proof. So start by just declaring all the variables. Proof. So let's let h sub n of x be given by the formula the sum from k equals 1 to n of x to the k over k factorial. We want to show that the sequence of functions, sorry for that sliding noise, h sub n is uniformly Cauchy. So from here I'm going to start following both the ideas that we had to the side, as well as kind of the sketch given in the piece of the notes themselves. So first let's well, we want to prove something is uniformly Cauchy, so let's start with this. Consider any epsilon bigger than 0. Now I need to come up with a choice of big N. So in the scratch walk off to the side, I found my choice of big N. My big choice of big N is whatever I need to get that to happen. So let's see, as given in the problem, or possibly as is given by the geometric series, the sequence u sub n given by the sum from k equals 1 up to n of 1 over 2 to the k is a Cauchy sequence of real numbers. Thus, let's see, I've already picked my choice of epsilon, right? There's the epsilon. My goal is to come up with my choice of big N. Thus, there exists a choice of big N such that for all m and n bigger than big N, the absolute value of u sub n minus u sub m is less than epsilon. Now, let us consider any m and n bigger than this particular choice of big N, and any x in the domain negative 1/2 to 1/2. Now I'm going to follow this stuff, basically just with some explanation added. So when you actually write down a proof, you need more words than just a string of equations. So the first thing that we did off to the side is we assumed that little n was bigger than little m. So let's do that. Without loss of generality, we will assume little n is bigger than or equal to little m, right? One of the two is the bigger of the two. May as well be little n. Then, well, we proceeded by just analyzing the absolute value of the difference. Absolute value of h sub n of x minus h sub m of x is equal to the sum from k equals 1 up to n of x to the k divided by k minus the sum from k equals 1 up to n of x to the k m rather than k. That's just by the definition of this sequence of functions. Now, let's see, the first thing we did in the argument off to the side is we did some cancellation. Equals the sum, absolute value still, from k equals m plus 1 up to n of x to the k divided by k. I just took those sums and I canceled the terms they had in common. And see, I know off to the side, well, no, let's do that. Let's use the triangle inequality next. Yeah, we have to use the triangle inequality. What I was about to say was just false. The sum from k equals m plus 1 up to n of absolute value of x to the k divided by k by the triangle inequality. All right, nice. Going back over here. The next thing I did is I said, well, I want to get rid of the x's. I know the absolute value of x is less than or equal to a half. It is less than or equal to the sum from k equals m plus 1 up to n of 1/2 to the k divided by k, because x is in negative 1/2 to 1/2, so that absolute value of x is less than or equal to 2. This is now, so the next thing we did is we erased this k so we could get something that looks like u sub n minus u sub m. So erasing that k, this is less than or equal to the sum from k equals m plus 1 up to n of 1 over 2 to the k because each of those k's is bigger than or equal to 1. Dividing by something that's bigger than or equal to 1 will just make it smaller, and everything's positive, so there's no danger of screwing up inequalities because something's negative. Alright, so now let's try to get back to this difference. In order to do that, let's just simplify u sub n minus u sub m and see what we get. So that'll be the sum, absolute values, of 1 over 2 to the k from 1 to n minus the sum from 1 to m of 1 over 2 to the k. That's the same as absolute value pairs, the sum from k equals m plus 1 up to n of 1 over 2 to the k. Those absolute value pairs don't matter. Everything in there is positive. Which is exactly what we see here. So that's everything, right? If I take this and just append this going backwards, I'll have my comparison with n minus um. So let's see, that is now equal to absolute value of the sum from k equals m plus 1 up to n, 1 over 2 to the k, everything inside is positive. That is the same thing as the sum from k equals 1 to n of 1 over 2 to the k minus the sum from k equals 1 to m of 1 over 2 to the k by adding in some canceling terms. That is now exactly the same thing as un minus um by the definition of un is less than epsilon. And here, we have to go all the way back to the top. What was our trace of big N? Our trace of big N gave us that. Since N and M are bigger than big N, and using our choice of big N. Now, closing statement. Thus, for all epsilon greater than 0, there exists a choice of big N. Notice I didn't ever explicitly give the choice of big N. I could have. Everything came from a formula. But I didn't need to. I just used the fact that there's something else that I know is Cauchy to, if you like, compare it to. Such that for all m and n bigger than big N, and for all x in negative 1/2 to 1/2, absolute value of h sub n of x minus h sub m of x is less than epsilon. Therefore, h sub n of x, well, h sub n is uniformly Cauchy on negative 1/2 to 1/2. And I'll include my little Halmos box that ends the proof. Let's address some conclusions, because you're asked to give some conclusions in your homework. So, since the sequence h sub n is uniformly Cauchy, it follows that h sub n is uniformly convergent. Let's let h be its uniform limit. Sorry, I had to put the cat down. Off of the table. Well, what's the point? Well, let's see. H sub n of x for any fixed n for any n in n, h sub n of x is, well, let's just expand it out. That's 1 plus x over 2 plus x squared over 3 plus da 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 plus x to the n over n is a polynomial. In particular, h sub n is continuous. So let's just close up as h from -1/2 to 1/2 is the uniform limit of a sequence of continuous functions h itself is continuous. Cool. So I'll go ahead and get this video posted. There's only one lecture remaining in this class, in which we will use the many of the tools that we've addressed so far to prove that power series are continuous on the interior of their intervals of convergence. I'll look forward to it. We'll talk to you again real soon.